So you have these very weird logical sort of contradictions, so to speak, but they're not really contradictions. And as Rafael pointed out in specific examples, you can show that when you apply the principle of primitivity, rather than get single fine-grained histories as possible realities, you could get groups, you could get collections of these histories as your and let me just end with the simple example of the three-slit experiment, three-slit Gedanken experiment. Okay.
So these collections would represent correlations for you?
Pardon?
Would they represent quantum correlations or something?
So you can get quantum correlations out of this.
Yes.
So this, but I don't have time to go through an example.
Is there a Bayes theorem for this version that provided A happens, what is the probability that B might happen?
We're not talking yet of probabilities, no? We're just talking about whether this is a possible history or not, whether this is a possible reality or not. Can this happen or can this not happen? So the idea of preclusion is tied in. I just don't have time to do this in very much detail, but we do want only so-called primitive preclusive coevents. And because we're using the multiplicative scheme, we also say they're primitive, preclusive, and multiplicative. So the primitivity tells me that as I look at this Boolean lattice, I look at the supports. And if I say, well, this may be the support of a coevent, of a primitive coevent, that is an actual reality, then I have to make sure it's not contained in a set of measure 0. Okay? Because if it was contained in a set of measure 0, although it may not be a set of measure 0, it is still not allowed in the scheme, because phi will still be 0. Phi on this will still be 0. So I have to look for something that is small enough in this lattice. I have to go down in this lattice as much as I can and make sure that that set is not a set of measure 0. So as Rafa pointed out in the case of the two-slit for a dark fringe, the union of 1 and 2 is 0. Therefore, neither 1 happens nor 2 happens. So basically, the reality of that is the photon doesn't go through. You know, that's how you would interpret that. So in the three-slit case, which is a little bit more complicated, so we have. So in that, so the three-way Boolean lattice, so sorry, I should write ABC. Okay, this is the three-way Boolean lattice. What I'm saying here is that AB doesn't happen, BC doesn't happen, right? Because if I add them together, it's a set of measure 0. Yeah? So AB doesn't happen, BC doesn't happen. AC can happen, but then if I look at any of the more primitive objects here, they're all contained in sets of measure 0. So the most primitive you can get here is this guy. So A doesn't happen, B doesn't happen, C doesn't happen, but AC happens. That pair of parts is the reality. So this is where, you know, it's a new conception of reality. But to me, it seems like a much nicer way of thinking about quantum theory than not being able to ask questions about what the quantum particle is doing. So I'll end there.
Can you tie these things together? Because I don't see the connection. So in the classical case, you needn't talk about covalence at all, right? If you just have the measure, you have the sample space, then you have a.
Well, you needn't talk about it, but you actually do, but without actually explicitly saying so. That's how I would like to think about it.
I mean, you have a sample space, then you have a measure on it, right? And then on these events, right? So every event you get some positive number, and you can either use this.
But you also want to make the statement about classical reality, right?
Right.
Suppose
So
you
those
have
events are questions, and you can ask.
No, you also want to make a statement about what is a fine-grained, what is a, if I have a realization, single realization, does the particle do, what does it do? I mean, not what does it do, does it do anything? What are the possible things it could do? It could be in this path, it could be in that path. That's the statement that one is trying to make precise. And it's something that I think, the thing is that it's something you just, why is it a fine-grained history? So let's ask the reverse question. Why do you think that a classical trajectory, just based on if you just started off with the sample space and the event algebra and even for a finite event algebra, why would you imagine that the events that in any given realization a particle does executes a particular path? Where do you get that from?
That's part of the setup, right?
So that's the point. It's
Classical
not part of
theory.
anything
You can make
that
it.
is.
You can put in an additional structure, but I don't see the.
It's not. It's
That
not
was not-
coming in. It's not coming
That
in.
wasn't my question.
Okay.
My question was in the quantum theory. You have this measure, the quantum measure. You have the sample space and the event algebra, and now you also, using the quantum measure, you can define this set of co-events, right? And so now, what are the roles of these different things?
So the thing is, some level one is dynamics. The omega, I mean, it's I would say maybe partial dynamics, but it depends on how you want to define dynamics. I mean, from a conservative point of view, I'd say this is the dynamics. Omega, A, and mu is the dynamics, and the other is how you interpret the dynamics. And I'm saying that classically we put in without knowing it, and I would say, well, if you just gave me the dynamics without giving me what a co-event is, I wouldn't be able to deduce that the particle executes a single path in any one given realization. I would not be able to deduce that. That's my claim.
Is the question what is the definition of a primitive co-event? Is that the question?
No, I mean, till one introduced the event algebra and so on, it was going very parallel with classical stochastic theory, right? And then, now, what is the role of the co-events vis-a-vis the events themselves? I mean,
So the
events
role of
are
the
no longer
co-event is to
primary
tell you that something happens or doesn't happen. That's just a general co-event. But you want to talk about co-events whose support, and I don't know how, support in the sense that I explained is the finest possible support without that object being precluded, okay, without it actually being contained in a set of measure zero. And that same thing that we've used, so let me just say this, that in a classical situation, in the classical case, you can use the same Boolean lattice. Okay? You'll have co-events with support here, here, here. Maybe this set is excluded, yeah, for whatever reason. This A and B is not allowed. But that you would then conclude that A and B are not allowed because of the homomorphism. But because AC is allowed, you would then conclude that C is allowed. So you would say there's just one path that just goes through C. And I'm saying that this is very much part and parcel of how we think of stochastic theories, except that it's almost never spelled out in precisely this way. And by spelling it out, you're now able to generalize, expand that to include this quantum measure, situations that arise in quantum theory. So, sorry, Rafael. So you have.
No, I agree. I mean, I wouldn't have said any, I would not say anything different. The only question is if that addressing your. I'm not sure I understood what your question was.
When you think of it, so maybe I should formulate the question.
I mean, to be fair, this is, I think, the trickiest part of the whole. This co-event structure is the trickiest part of the
Supposing,
interpretation.
I basically adopted, suppose I went to classical theory with a, what you call the frequentist kind of interpretation, then I have some events which are my questions, and then I say whether with some probability which is given by the measure, whether this occurs, doesn't occur, etc. And everything is now clear to me. Now I have the quantum measure, and I have these events, but of course I can't take the view that I can ask whether this event occurred and assign a probability given by the quantum measure. I don't know what the interpretation is that way because of some rules being violated. So, but now I'm still grappling with what do the co-events.
So that's the thing that
Mu is not defined.
even in the
space of
first
co-events,
case, even
right?
in the first case, I would say that you did not even get to the point of interpreting the classical probability. You just stayed with the functionals viewpoint.
Well,
Does this happen? Does not that not happen?
you just said at some point, everything is clear. But that statement that when you're talking about the classical situation, you said there's these events, each event has a probability.
Yes.
Either it happens or it doesn't happen, everything is clear. All that Sumati is talking about in all the function of the co-event is sort of to fill in that statement, everything is clear. How does it get filled in? I'm just repeating what you said. How does it get filled in the classical setting? And how does it get filled in the quantum setting? And the difference is that in the classical setting, everything is still coming from preclusions, although there's this issue of proximate preclusion and so on. Everything is coming from preclusions, but the kind of patterns of preclusion that are possible are limited because of the absence of interference. In the quantum case, new patterns of preclusion are possible that are not possible classically. So for example, it can happen that the precluded events completely cover the sample space, the history space. So that classically you would have said there's no possible reality. So in the face of that kind of thing, what would be the potential realities? They're no longer just the individual histories or the individual points of the sample space. So what are they? So when somebody is saying, well, let's go back to the classical world, think in terms of events, not in terms directly of, don't jump to the conclusion that reality has a single history, but just think in terms of events. Then what would be a complete description of reality? Well, it would tell you for each possible event whether that event actually happens or not. Right? So for every question that you can ask about the world, which is an event in the technical sense, which is the question whether that particular event happens or doesn't happen. And for every possible question that you could ask, you could be given the answer, then you would have a complete description of reality. Now classically that complete description of reality is, we assume it's given by just naming a particular history and saying those events happen which contain that history, and those events don't happen which don't contain that history. So it's a kind of dualization. Given a point of the sample space, you get a map of it's called the evaluation map sometimes. You get a map of the set of events, of the event algebra into Z2, into the true-false thing. So the idea is in quantum mechanics, that's what you want to keep as your description of reality. A complete description of reality will be again the same thing. It'll be an answer to every possible question you could have asked. But the pattern of the answers that are allowed is different in the quantum case than in the classical case. Because you couldn't have, like in that case we saw where the whole history space is covered by precluded events, no matter what history you would name, if you say this represents the reality, you get in trouble because then it implies that certain events happen which cannot happen because they're of measure zero. So what do you do instead of that? And then in this multiplicative scheme, what you do instead of that is you say, we'll keep the fact, this kind of this kind of, I don't know what to call it, but we'll keep this fact that with specify some, instead of single history, some set of histories, and we say that an event happens if and only if it contains that special set of history, which is somebody was going to support as a co-event. So a co-event will still be described by something rather similar. Instead of an individual history, it'll be a set of histories. And once you have that set, it tells you for every, that support, it tells you for every event whether or not that event happened. So it's a complete description of a reality. So when is it a viable description? When is it a dynamically allowed description of reality? And the answer is when that support is as small as possible without coming into conflict with the preclusion principle. So in other words, I couldn't choose a single history.
Like this one, yeah.
Because no matter for which history I chose, I find some precluded event that contains it, let's say in that extreme case. But it might be that I can choose two histories, and then between them, no precluded event contains both of them. And so they can represent the reality. That's the co-event. That's the idea of the multiplicative scheme. It might be that I need three. In this case, you only needed two. It might need you needed three. So you're sticking as close to classical logic or the classical setup as possible without coming into conflict with the preclusion principle. And then if you do all that and you say, now let's suppose I go back to a classical situation where the patterns of preclusion are only classical, which basically means that any subset of a precluded subset is also precluded. More precisely, any set covered by precluded sets is also precluded. If you limit yourself to that situation, which will always be the one that comes out of a probability, a classical probability, then you can prove as a theorem that the primitive co-events do correspond one-to-one with the individual histories.
So I guess
At least in the finite case. In the infinite case, there's a technical subtlety. But let's forget.
in the classical case, I could, I could make the statement, right, that the sample space is the space of primitive co-events, right? So I can just directly deal with primitive co-events. But in the quantum case, I need this auxiliary. Is it necessary to have the sample space as a necessary auxiliary structure, or can I just directly talk about primitive co-events and base everything
How would you do
on
it?
that? No, I'm just asking
You
because
could-
the classical
Actually,
theorem seems I
event
can't, right?
algebra.
Once you had this Boolean algebra, this event algebra, then you could not
You could-
talk
Wait,
anymore
wait.
about the sample space. But you, in order to compute, to know which events are actually precluded, you need to do some sort of path integral or something that involves the sample space. But if I give you, for some reason, which are the precluded events, and give you the event algebra, then from that you could deduce. I'm leaving aside technical subtleties that come in the infinite case, but at least in the finite case, you could deduce everything just from that.
I just want to make one remark, which is that
I'm just turning it around so that one can only talk in terms of what is quantum mechanical behavior.
But how would you talk? Yes, I'm not
So
sure. I
there's a
fully
way of
understand.
getting it, but then when everything is clear, maybe you can talk about it.
So I just want to say one thing about this idea of having sort of generalizing to say pairs of parts or collections of parts. Something that Rafael just said a little bit about, but I'll just say it in a more cartoon way, that if you think of a classical fine-grained history as actually deeply just being a coarse graining of something which is a more finer set of histories, then what this is saying to you is that, well, it's not that even that you're going to a finer class than what the coarse-grained history that the classical history really deeply represents. But then rather than come to the most fine-grained history, you have something a little bit more relaxed. So what is very nice here is that even in terms of the picture of reality, in terms of fine-grained to this slightly less fine-grained picture, is again a beautiful sort of, in terms of just the generalization, you can picture it immediately. So this generalization of reality is going from an actual fine-grained history to a collection of fine-grained histories is, in some sense, as weak a condition as you can, as weak a condition that you can. I'm not sure whether I should use weak or strong, but yeah, the weak, just a slight weakening of classicality in some sense, from this logic point of view. So, and that by keeping to one of these schemes, you do that. You stick to some particular.
So I'm saying that by post-training we regain one of those nodes.
Right. So that's what Rafael said. That if you put in certain class of conditions, then you could regain classicality by coarse-graining and requiring that those coarse-grained sets satisfy certain conditions. Then those coarse-grained sets themselves would satisfy the homomorphism. So what you would get is a sub-Boolean algebra of sub-algebra of events corresponding to the coarse-grained set. And those would satisfy through this. But you need a set of conditions for those. I mean, is that right? Yeah. I'm trying to be as imprecise as possible.
Now regarding this, back to the example of the three state. So AB doesn't happen, BC doesn't happen, which means A, B and C don't happen, but AC happens. So how do we see this physically? What actually is the particle doing?
It was going through both slits.
It's going through both slits at the same
Something
time.
you know already about.
You can put words on it,
Yeah.
that's one set of words.
Yeah, but do you prefer that set of words?
I have mixed feelings about it.
Oh, yeah,
'Cause I think in one way it correctly represents the idea. In the other way, it sounds like
Particle is not indivisible anymore.
it sounds like you want to say, if I say the particle goes through both slits, then you might want to take that to imply that it goes through this slit and it goes through this slit. But that's of course not true, because we're saying that A does not happen and C does not happen.
Exactly.
So there's a little, I think, danger in using that language. But there's a danger in using almost any language. Because whenever you use any language, you always assume you're using the usual logical relationships among the different sentences. And somehow that's not the case here. So a safer thing would be to say that the reality is some sort of a blend of two histories, one of which it goes through A and the other one in which it goes through B. Neither one represents reality, but those two together represent it. That's a kind of long-winded thing. It's quicker to say it goes through both sides.
No, it's just curious whether one can go even at a deeper level, think of further generalization of the algebra to make this kind of class of questions even more precise.
I mean, there's a kind of curious thing. You can represent any co-event as a polynomial in histories. I haven't explained at all. I mean, I'll just say that. To explain it takes a little while. This particular one would be a monomial, but just the product of those two histories, A and C. But I just say it to indicate that reality, or a description of reality from this point of view, is not represented, not given by a single history, it's given by some sort of combination of histories. And that combination, in the most general case, in any scheme whatsoever, can be represented as a polynomial. So reality is somehow built out of histories, but not in the way that it's built out of histories classically. Classically, it's built out of histories in the most simple-minded way, that any given reality is a single history. Here it's built out of histories in a more subtle way. And in the multiplicative scheme, it's just a very mild generalization, as somebody said, that reality, instead of just being a single history, is a set of histories. And we choose that set small enough to comply with the preclusion principle, but no bigger than you need in order to comply with it. And it's a very natural. In fact, I mean, there's a mathematical language for those who know it. You can say in the multiplicative scheme, the set of events which happen, for a given co-event, the set of events which happen form what's called a filter. And But it has to be a preclusive filter, that is, it must not include, I just say this for those who know the definition, it must not include any precluded events. And then reality is, or a primitive covariant is a maximal preclusive filter. If you say that in the classical case and you say that in the quantum case, it's exactly the same rule. But in the classical case, it gives you an individual history. In the quantum case, it gives you this kind of multiplicative co-event that Sumiti talked about. So I don't expect most people to know exactly what all those words mean, but it's just a way of indicating how mild is the generalization that's going on between in passing. If you formulate the classical rules in the right way, then the exact same words apply to the quantum case, and all that's changed is the type of the patterns of preclusion which can happen due to interference.
So, I mean, as an example, which the kinds of, I mean, for someone who's, the person interested in quantum gravity, here is a way in which you can actually ask about possible realities that, say, the universe took, I mean, possible parts of the universe took, or the possible histories that, of possible realities of the history of the universe. So let me say that again. If you're in quantum gravity, there are no external observers, so you want to describe everything in terms of in this language of closed systems, which is what this is. There's no external observer telling you this happens or that happens. There's no measuring device. And so here you're going to say, well, you can put a measure on the space of histories and you can get quantum, so whatever your favorite quantum theory, you put a quantum measure on the space of histories. But you want to say, well, something happened, or this was a possible history. This was a possible history. This history could not have happened. This space-time could not have happened. Did the space-time inflate, just suddenly get created and become infinitely huge right away? What is a measure on that? So these are the kinds of questions people in cosmology, quantum cosmology, are always interested in. But there's no way of answering them because you have, first of all, you have a singular event, and so you have to, and you don't know how to interpret these probabilities. In fact, I think a lot of what people do in inflationary theories is related to understanding what these measures mean, even from.
Well, now they're completely stuck. They have this landscape, and they.
Yes. So.
What is it? I think they call it the measure problem, or something.
Yes.
Which is how to put a measure on, which is how to employ probabilistic language to talk about an infinite universe with infinitely many copies of everything happening infinitely many times, infinitely many possibilities for vacuum, or virtually infinitely many. So
It just seems that at some level
actually,
this.
they're not even yet grappling with the quantum problem, because that whole discussion is usually carried out in the semi-classical setting. Yeah, so I think let's maybe just to take your example of inflation. Did inflation happen or not? That's a question that you could ask. And if someone would tell you a single space-time, a single Fourier geometry, then the answer would be clear. But quantum gravity will not be giving you that. But suppose it gives you a set of Fourier geometries, then you just examine that set. If all of them look roughly like an inflating universe, but just some fine details different, then you have some semi-classical space-time, and the answer is yes, inflation happened, and it happened in this particular way.
And that's the co-event.
That's the co-event.
And
If the co-event is supported on space-times, all of which showed the same sort of inflation, then the answer would be yes. But if it was supported on a combination of histories, space-times, one of which had inflating and the other one wasn't inflation, then you'd have to answer that the inflation did not happen from this point of view.
So why do you call it a scheme? Are there some examples where things don't work? Or?
So sorry. So this one, if you just took the linear, they're not exact. So it's a choice. It's a choice because you've got classically you have a homomorphism, satisfies these two rules.
But
if you pick one and you can't pick both, essentially because there are quantum mechanical situations in which you can explicitly show that both cannot be satisfied. So if you picked one, that's a scheme, it's a choice.
Yeah, but I mean, is that choice